I've started recording, and our first talk for today is geometric recursion. The talk will be given by Jørgen Andersen, Center for Quantum Mechanics in Denmark, and this is a joint work with Gaëtan Borot and Nicolas Corentin.
So thank you very much for inviting me to give you this talk. And sorry to just have to correct the chairman right from the get-go, but that's very important because this is not Center for Quantum Mathematics, sorry, Quantum Mechanics, as you said. This is Center for Quantum Mathematics, which I think of as something different, though related. Anyway, thank you. So indeed, this is a joint work with Gaëtan Borot and Nicolas Corentin, and it is about our common geometric recursion. And so let me try to get into it. So there are 13 sub-chapters to this talk, but I will skip some of them, go lightly over some other ones. So I think we simply just get started. So don't worry about reading all of these, but let's get started. So the setting I want to tell you about is something called pre-target theories. So a pre-target theory is the following. First, I consider S here, which is the category of compact-oriented surfaces. And the morphisms in this category are isotopic classes of diffeomorphisms. But first go, the target of the category of this functor is the category of vector spaces. So I'll try to somehow give you a mild version first and then gradually get into precise definition. And then we are asked that also that there is a functor E from the category S to the category V. And such a functor we will call a pre-target theory. So in other words, it's something that associates vector spaces to surfaces in a functorial way. Okay, so what the game of geometric recursion is to really produce a functorial assignment of omega sigma inside the vector space associated to sigma for every surface, so for every object in S. And we want this whole thing to be functorial, of course. And so that in particular means that this omega sigma will not just lie in this vector space, but it will lie in the subspace that is invariant under the Markov class group. And so that's a very important point about this whole construction here. Okay, I move on further. So it's actually amazing that in this very, very simple setup here, there are really a lot of different construction in geometry and topology in low dimensions that fits into this framework. So let me show you a few of them, which will be particularly relevant for this talk. So the first one, maybe I do like this so you can see it. Can you somehow see the last line as well now?
Yes.
Okay. So the first one is very, very simple. It's just the continuous functions on Teichmüller spaces. So T sigma is the Teichmüller space of sigma. I consider the continuous functions on Teichmüller space. And now I simply select the function 1 on each of the Teichmüller spaces. Obviously, it's mapping class group invariant. And so that's an example. It's the most boring example, but it will actually play an interesting role for us. Now, the second example is much more interesting. It is the sum over all simple closed multi-curves as functions on Teichmüller space. So the pre-target theory is the same. We take continuous functions on Teichmüller space, but now we take considerably more interesting functions. So we take S sigma here to be multi-curves. So that is the set of isotopic classes of embedded closed one-dimensional submanifolds in sigma, such that no component is isotopic to a boundary component, nor are any two different components isotopic. And so it's a sum over that set. And for each gamma, we take a product over the components. So this can have several components, right? Take a product over the components. And then we apply some sufficiently fast decaying function to the lengths of the components. And the length is computed with respect to a point in Teichmüller space. And so this is the way this whole infinite sum of products becomes a function on Teichmüller space. And so this function here has to decay sufficiently fast for this to be a nice function on Teichmüller space, of course. And if it decays sufficiently fast, then all the mapping class group action will do is just permute the sum here. And so therefore, if it decays so fast that we have absolute convergence, of course, we will get that this is a mapping class group invariant function on Teichmüller space. So this is a very interesting function. It has to do with statistics of simple closed curves on surfaces.
Sir,
yes,
Jürgen,
yeah.
Do you mean that you take the length of a geodesic, which is
yeah, that's what I mean. So there's a natural function which takes, the geodesic. There's a unique geodesic in each homotopy or isotopy class of a simple closed curve, and so I take the lengths with respect to that geodesic length. Okay. Now there's another source of interesting functions on Teichmüller space. So the target theory is the same, pre-target theory is this, just continuous function on Teichmüller space. But now I take a different function. I namely, for each sigma in Teichmüller space, I take the Dirichlet or Neumann Laplace-Beltrami operator on this Riemann surface, which of course depends on where I am in Teichmüller space. I then apply some function to it again, which has sufficiently fast decay at infinity, and then I take the trace of that. So a typical example you can think of is if f here is the exponential function, then this is the heat kernel of the Dirichlet or Neumann Laplace-Beltrami operator. And so that's also a very interesting function. Okay, let me give you a fourth example, which isn't functions. So now I will switch to a different vector space. So to do that, I just have to introduce a little setup. So sigma here is a surface, compact surface with boundary, right? And so I consider Teichmüller space of it. And of course, I think of this as hyperbolic metrics on the surface with geodesic boundaries. And so there is this preferred length of the boundaries. And so I can split this into a union over, all the Teichmüller spaces where I have fixed the length of the boundaries. That's what it says here. Now what I will consider is, I will consider omega by Petersen. This is going up depending on L. And so it's a 2 form on the Teichmüller space where I fix the length of the boundaries to be L. And this is the Weil-Petersen symplectic form. And so if I'm given a pair Pans decomposition of the surface sigma, I have global French-Nielsen coordinates on that Teichmüller space, which is Li theta I, where the index runs from 1 up to 3t minus 3 plus n. G is the genus of the surface, and n is the number of boundary components. And then the Weil-Petersen symplectic form is given exactly like this. And so one thing I could consider is I could just consider 2 forms, but maybe I will even consider all forms in Teichmüller spaces. And then I will take the exponential with respect to the wedge product of this 2 form. So that starts with the function 1, then it has the 2 form itself, then it has the 2 form wedged with itself in degree 4, and so on, all the way up to the volume form associated to the Weil-Petersen symplectic form on Teichmüller space. Okay, so these are examples of such target theories. And now let me try to be a little bit more specific about which precise category of surfaces I want to consider. And so actually I want to have in mind 2 variants of this theory. But what's going to be common to all of it is that I am going to consider, at least in the first part of the talk, compact oriented surfaces of negative Euler characteristic. So they are smooth surfaces but with boundary. And then I might have mark points on each of the boundary components. So I will consider both the theory where I don't have that and where I have it, together with an orientation of the boundary in such a way that the boundary is naturally split into the in boundary and the out boundary. And I want it exactly such that there is one in boundary for each connected component of the surface. And that can be said in the following way, that if you consider the part of the boundary that's in and look at the inclusion into the surface, that gives you an isomorphism on connected components. So those are the surfaces I'm going to consider. And then morphisms, this is going to be isotopy classes, orientation preserving diffeomorphisms, which preserves mark points if they are there. Else they preserve the orientation on the boundary as well. Modulo isotopies, which preserves that structure. That's the precise set of surfaces and the category of surfaces that I want to consider. Okay, very good. So now what I want to do is I want to specify a little bit more data about what kind of target category do I have in mind. Now, as you saw before, I took something like continuous functions on tight molar spaces. These are infinite dimensional vector spaces, and therefore I'm bound to have to do some kind of analysis. So I need some kind of analytic tools on my vector spaces. And the appropriate thing to consider is Hausdorff complete locally convex topological vector spaces over the complex numbers. So these are vector spaces whose topology are given by a stack of semi-norms. Okay. And then morphisms are just morphisms of such, so morphisms of locally convex topological vector spaces. And so a pre-target theory is simply a functor E from surfaces to this kind of vector spaces. So functorial assignment of such a topological vector space to every surface. Okay, so now we assume we have such a functor, and then here's the basic idea behind geometric recursion. Basic idea is that we start with this functor, and we would like now for every surface to assign in the functorial way a vector inside the vector space of the surface, mapping class group invariant part, and we want to do this recursing in the Euler characteristic. And what do we recurse by? Well, we recurse by extracting pair appends from surfaces. But see, this is not going to give us a finite sum if we do this, right? Because there are infinitely many ways of embedding a pair appends into a surface. Even if I ask that I embed only the pair appends in such a way that it definitely contains the in boundary. So if I constrain that it always have to contain a specific boundary component in the image of the pair appends, of course, there's still lots of possibilities. There's countably many, but there's certainly not finitely many. It's just countably many. Okay, but that's good. We're going to attempt to perform some sum over this set of pair appends, up to isotopy, of course. So basic idea is we take a pair appends, we excise the pair appends, so we cut out the pair appends. Then the idea is that we have something assigned already to the pair appends. We assume that what remains, well, that has Euler characteristic one bigger than what we started with now. So we assume we already have built a vector for the remaining part, and then we somehow glue something assigned to the pair appends and what's in the complement together, and then we sum over all possibilities. That's the main idea. There's also another case, and that is we also stop at one-hole tori. One could also cut the one-hole tori into pair appends, but we will leave that untouched for the moment. So those are the two surfaces of Euler characteristic -1, which is a pair appends and the torus, right? And so everything else has lower Euler characteristic. So the process will slowly work up towards Euler characteristic -1. So what am I asking for? Well, I definitely am asking for this pre-target theory to be given. But I also need a disjoint union morphism. So that means that if I have something in the vector space associated to one surface and something associated to another surface, I would like to be able to deduce something associated to both surfaces. So that's the disjoint morphism. It's just a linear map like this. And gluing morphisms are also important, as I just discussed. So if I have some out boundaries on the first surface I want to glue to some in-boundaries of the second surface, then I should be equipped with a gluing morphism, which takes a vector from the first vector space, from the vector space of the first surface, and a vector from the vector space of the second surface, and performs the gluing. So it gives me a linear map that gives me a vector in the glued surface. Because if I have that, then I can ask that I have starting data, which is I have some specific vector in the pair of pants vector space, invariant under the mapping class group of the pair of pants. I have some D, which is in the torus vector space, also invariant under the mapping class group of the torus. And then my initial starting point is just omega P will be A and omega T will be D. But now I also need recursion kernels. So I also need a B, which will actually depend on the choice of the two out boundaries that a pair of pants has, and then a C, which is symmetric in the two out of a pair of pants. And now what I do is I simply just sum over all pair of pants. And of course, pair of pants come in different types. So there's what we call the B type and the C type. The B type has two boundary components in common with the surface and one interior. And the C type has only one boundary in common with the big surface I'm embedding into it, and then two interior. And of course, there is also two further cases for C. The complement can be connected or it can be disconnected. But we will use the same C for those two cases, although we could vary that if you want. But this is so that it aligns well with topological recursion. And now our attempt is simply to say, very good, we will sum over all pair pants of type B. We will apply the gluing map to this recursion kernel combined with what we already have constructed, because this has Euler characteristic 1 bigger when we remove this pair pants, plus all the pair pants of type C, stick in the C recursion kernel in the gluing map and combine it with what we have already defined for a higher Euler characteristic surface. And here this integrating set is the set of isotopy classes of embeddings of pair pants into sigma of type B and C respectively. So you can of course see that we require some analysis to do this, because these are infinite sums. They are countable sums though. And so what we need to do is somehow have some axioms, some decay axioms on these quantities here, such that these two sums here become absolutely convergent. And if they're absolutely convergent, everything is perfect, because then mapping classes will just permute these two sets here inside them. And so therefore this guy here will actually be a mapping class group invariant as wished for. Okay, so that's the main setup of geometric recursion. And let me just tell you the setup, in other words. So it starts with initial data, which is this A, B, C, D, where A and C are in the vector space of a pair of pants. B is and C are also, B is and C are also, A and C lie in the mapping class group invariant part. B does not have to be mapping class group, but it has to have this transformation property here. And then D is in the mapping class group invariant part. And then I will get to in a second what it means to be admissible for initial data. So initial data that satisfies certain norm estimates with respect to all of these semi-norms we haven't really touched on yet. So they decay appropriately. And if we have such a setup, then we get this main construction and theorem here. So we run the formula you saw before on the initial setup that the pair pants is A, the torus gets D, and for all other surfaces of Euler characteristic less than -2, we recursively define it via this recursion formula we just discussed in detail for closed surface, for connected surface, and for disconnected surfaces we just use this disjoint union morphisms to define them. And then the main theorem of this whole game is that this assignment is well defined. More precisely, the above series defining omega sigma here is absolutely convergent for any of the semi-norms that we have on these vector spaces here, and it's functorial in its mapping class group invariant. Okay, so I could choose to go through the absolute precise definition of a target theory for you here. But I think what I will do is initially skip this precise definition of everything and set up with all the semi-norms and so on. And I will attempt to come back to this in the end. Okay. So what I will do is I will, so here I'm showing you exactly, all the estimates that needs to be satisfied and so on. I will come back to this in the end because I want to try to show you an example, namely continuous functions on tight Miller spaces before I do this. But just a few remarks. So how does this fit into the picture of topological recursion, quantum area structures, and geometric recursion? So topological recursion, as all of you know, was invented by Chekhov, Vinard, and Andersen in about 2005 to 7, written up by Vinard and Andersen, and it takes as its input a spectral curve, and it produces these for non-negative integers G and N. It produces from the spectral curve recursively forms, and the whole structure is totally reminiscent of the irreducible components of the boundary of MGN. And after that, about some 10 years later, a little bit more, quantum area structures was introduced by Kontsevich and Selberg in 2016-17. And that takes as its input 4 tensors, A, B, C, D. And so this is somehow inspired here by this notation here that we also use A, B, C, D here. And then it's, this data here really specifies and quantifies a certain quantization of a Lagrangian. And then any initial data of a TR, one can construct ABCD, which gives a quantum area structure. And then the output of TR becomes encoded in this Kontsevich-Selberg general construction of a quantization of a quadratic Lagrangian. And so the geometric recursion is really somehow, well, inspired in part by quantum area structures in the way they were set up, but it really took its origin in topological recursion because what we really wanted to somehow very clearly show that G and N in topological recursion really has a manifest interpretation as the genus and number of boundary components for a surface. And so you see that in geometric recursion, it's completely manifest that there are surfaces, and now there is actually functorial behavior in these surfaces. And yeah, so that's sort of what it says here. And then actually you will see that there is a way to map any example of GR for the target theory of continuous functions to topological recursion by integration over moduli space. And there's even a way to go back. So for every instance of topological recursion, there's a way to recover geometric recursion out of it in such a way that when you integrate over moduli space, you come back to the topological recursion. But so I stress that geometric recursion really a very different gadget than the 2 previous ones in the sense that it in some sense categorifies topological recursion. I mean, it becomes a functorial construction that can construct geometric objects on various spaces associated to surfaces. Okay, so let me actually show you specific examples. So let's take the target theory of continuous functions on tight Miller space. And so I want to discuss 2 versions of it in parallel. So my objects here will be compact oriented surfaces with boundary, as I introduced in the beginning, all of that, right? And I may or may not have mark points. But if I have the mark points, I will definitely take those into consideration. And so I can introduce tight Miller space of the surface. This is simply, all markings of bordered Riemann surfaces by this surface. So all diffeomorphisms from the surface to a bordered Riemann surface. And such 2 are equivalent if and only if there exists a biholomorphism from S1 to S2 in such a way that when I do this composite around, this restricts to the identity on the mark points if they are there, but it's always required to be isotopic to the identity. And of course, it should be a via diffeomorphism restricts to the identity on the set of mark points if they're there. And so what's the difference here with the mark points or not? Yes? Yeah?
Do you allow a single mark point at each connected component of the boundary? Or
Yeah,
several
yes.
ones?
No. In this, right now, there's 1 mark point per boundary component.
Yeah.
Okay, so if they're there, there's exactly one mark point per boundary component. If they are not there, yeah, no discussion. And so there, it's rather simple way that the two Teichmuller spaces. So if you look at the ordinary Teichmuller space, what I call ordinary is just that there's no mark points. So, but the same definition here, right? Then the thing is that there is a projection where you just forget about the mark points, and that becomes actually an R to the number of boundary components bundle over the Teichmuller space where there are no mark points. But if you look at the group delta sigma, which is the Dehn-Twist that are parallel to the boundary, then they act freely on this bigger Teichmuller space. And if you mod out by that group, what will happen is that you now still have something that fibers over the usual Teichmuller space, but the fibers are now, circles, and there is a circle bundle, and there is a circle per number of boundary components. So if there are n boundary components, it's U1 to the n fibers here over that guy. Okay, so those are the Teichmuller spaces I'm interested in. Very good. So now we want, of course, functions on this. So now I introduce the following subset. So I look at Teichmuller space. Now I just look at the usual Teichmuller space. And I require that the systole, so the length of the shortest geodesic in the interior of the surface, of the shortest simple closed geodesic, sorry, is bigger than epsilon. And I also require that all the lengths of the boundaries are also bigger than epsilon. And then I take E epsilon to be the continuous functions on that subset of Teichmuller space. And now what I want to do is I want to specify a set of semi-norms on that vector space. And in this case here, they're actually got to be indexed by exactly, points in this Teichmuller space here. And so what you can see immediately, of course, is that you have this epsilon parameter, and let's say it runs from 0 to 1. So I have some directed set, namely this interval from 0 to 1. And since these are sort of an exhaustion of Teichmuller space, I will get these restriction maps from continuous function in a larger one to a smaller one. And of course, it's clear that the projective limit of all of this is all of continuous functions on Teichmuller space. So this is kind of a technical gadget I need in order to make this all work. But now if I went through the details of the axioms before, you would have seen that I needed to require to have some set. For each epsilon in this directed set, I have to have some set that indexes semi-norms. And in this case here, indeed, what I have is I simply just take the length function with respect to that point in Teichmuller space as a length function. Okay, so this gives a length function on the set of simple closed curves on the surface. And I need this in order to make sense of the whole thing. But I also need semi-norms on these vector spaces here. And the semi-norms that I will take is simply the supremum norm over some compact subset of that Teichmuller space. And this compact subset is simply just basically a ball of radius 1. And so it's simply, it's a little bit technically defined, but you take the supremum over all simple closed curves on the surface, then you take the absolute value of the log of the quotient of the length with respect to the 2, where sigma is varying in little neighborhood of sigma. There should have been an epsilon here, sorry. You require this to be less than 2. This is essentially just a ball of radius 1 in the Teichmuller metric around that point. And so you take the supremum norm over those compact subsets. And that, of course, gives you the semi-norms, that gives you the topology, usual topology on continuous functions on this systole set of the Teichmuller space. And then there's a couple of axioms that needs to be satisfied. And the important parts here are simply that if you look at the simple closed curves on the surface, whose length is bounded by some L, then that should grow no more than a polynomial. And I mean, that follows from Marine's work, right, which was refined by Mirzakhani, and we call that the polynomial growth axiom. And then there's a further one that there shouldn't be too many, there should only be finitely many, what we call small pair pans, I will get into that if I get to the precise axioms of our theory. But Hugo Pallier have proved that axiom for us. Actually, it was proved prior to us looking at this. Okay, so that's the setup for this with the semi-norms precisely. And now I consider details of this target theory for pair pans. So of course, the usual pair pans Teichmüller space is just R plus to the 3, just the length, the geodesic length of the boundaries. And my bigger Teichmüller space is simply just R plus cross R to the 3. When I divide out by the Dean-Swiss that are parallel to the boundary, I just get R plus cross U1 to the 3. And that has actually that sort of analog of French and Nielsen coordinates on it, this guy here. So here the lengths are from here, and the theta i's are from the faces here. Okay, so now I need to produce some gluing maps, right? So I needed to, of course, be able to glue things together, as I was explaining in the beginning, to make the construction. So suppose I have again out of the first surface, in of the next surface, which I want to glue. So I have a couple of boundary components that I want to glue on. Then what I can do is I can look inside the Teichmüller space of disjoint union. I can look at the subset on which the lengths of the boundaries pairs that I want to glue on agree. So that's what I call this with this notation here. And I have the inclusion map of that into the full set, into the full Teichmüller space. And then the thing is that when I consider that and I divide by the Dean-Swiss in those boundaries that I'm gluing on, then I actually get a fibration over the Teichmüller space of the glued surface, which is a U1 to the number of pairs that I'm gluing on bundle. Okay, so this is the two structures I have. I will come back to these two structures a little later because it's actually simpler if I'm just considering continuous functions, because the disjoint union morphism is simply just obtained by saying, well, if I take Teichmüller space of two disjoint union of two surfaces, that's just a cross product of the Teichmüller space. So I have two projections onto the two factors. So I just pull back functions with respect to the two projection maps and I can multiply them. That's the disjoint union morphism. And if I want a gluing morphism, well, I simply just take two functions, each of their Teichmüller spaces. Then I take a point in Teichmüller space on the glued surface, and I simply just restrict to the two parts that are being glued together, and I just evaluate the product of the two functions. So these two maps are very, very simple. They satisfy what they need to do in terms of continuity of semi-norms and so on. And now my initial data I have to specify is simply two continuous functions, which are mapping class group invariant for Teichmüller space of a pair pans. I have to specify the recursion kernel B, and of course I have to specify D on a one-hole torus. And the precise admissibility condition, so the growth that I can allow for these functions, is described here. So it says that for all epsilon bigger than 0 exists a t bigger than 0, such that for all s bigger than 0, there must exist constants depends on epsilon and s, such that these inequalities hold here. So A grows like, powers of L's, which is specified by this T. Similarly, for the ins, for the exterior boundaries of B, divided by this little thing here, which has to do with small pair pans, and likewise for this, and then there is this one here also. So essentially some polynomial growth in the length variables. Okay, so the thing is, do we have examples of this? And indeed, yes, there is a very, very nice example of this, which is we call Mirzakhani-McShane initial data. And so it's simply because these functions come straight out of Mirzakhani's work. And so if you take the function 1 for A, you take this guy for B and this guy for C, and you define D to be the sum of all ways to split a one-hole torus into a pair of pans, and you apply this C here to the three lengths you obtain. Then those guys satisfy our analytic estimates I just showed you before, these ones here, and we can run the geometric recursion, and the geometric recursion gives you the function 1. So you can think of this as a partition of unity, and the proof is just replying over and over again the Mirzakhani-McShane argument you know, so her proof of the McShane identity. But it's really a, you know, splitting of the unit function into not functions with compact support as you normally do, but some kind of partition of unity relative to this geometric recursion scheme. Okay, there is a way to actually introduce a scale of this initial data. Some beta, you just multiply the length by beta, and you look at the limit as beta goes to infinity. And if you do this to Miyazaki's initial data, you will get Konsevich's, what we call Konsevich's initial data, which is something very simple functions, which you see right here. But these functions actually, when you apply our geometric recursion to it, gives very interesting result, right? It gives continuous functions on moduli space with the property that if you multiply them onto the Peterson volume form on these moduli spaces where you kept the boundary lengths fixed and you integrate them, what you get is simply just integrals over mgn bar of x of, you know, li squared half times the psi I classes. And so this is the reason why we call them Konsevich initial data. Okay, now let's see some more interesting functions on Teichmuller space we can obtain. So let's come back to this thing about summing over multicurves. So let's assume that f is some continuous function, and we will assume some fast decay very soon, right here. But at any rate, what we do is we consider all multicurves on the surface. So simple, you know, disjoint unions of simple closed curves on the surface up to isotopy. We sum over all such, we take the product of all components, we apply f to the length of the curves. So this becomes a function on Teichmuller space, provided that f decays fast enough. And in fact, if it beats all powers of L like this, that's sufficient. And so this will, if this condition is satisfied, this here will be continuous functions on Teichmuller spaces. And so we do this for connected surfaces, and for disconnected surfaces, we simply just multiply over the components, and then for pair pants, we set the function equal to 1. And so what we now do is that we would like to see, can we actually obtain this function here by geometric recursion? The answer is yes, we can. And the way you should do it is you should do what we call f-twisting of the Miyazaki-McShane initial data. So you don't do anything on A, right? Because A was also 1 before Miyazaki, so you just let A be continuously be 1. But what you do is you take Miyazaki-McShane's initial data B, and then you add f of the interior lengths to it. And on the C, you do the following combination. So you symmetrize this thing here where you multiply f onto b, and then eventually you also multiply the two lengths, f of the two lengths of the two interior boundaries for the C. And for D, you simply just take the definition of the function. And now the theorem is, when we apply geometric recursion to this initial data, we actually get this function here. So this is showing you that with geometric recursion, you can get very interesting functions on Teichmuller spaces. Okay, yeah, I don't really want to talk much about the proof of why this is the case. And I want to definitely cover something about OpenGR. So I will go rather quickly over the next few slides. So what we can do is that if you have a function, just as we saw before with the Konsevich case, if you have a function on Teichmuller space, which is Markov class group invariant, then it will induce a function on moduli space. Let's assume it's continuous. Then we can multiply it onto the Peterson volume form. And if this integral is finite, we can definitely define this function that just depends on the boundary length this way, just the integral. The thing is that if we do this to this function we just defined before, so if we do it to these functions here, these function here, then indeed the theorem says that there is a recursion for these averages, which is just like topological recursion, right? It sums exactly the same kind of sums as topological recursion. And now it is just using these functions, these kernels, recursion kernels that we had before, but now we just think of them as functions of 3 variables, and all you need to know is just the behavior in the boundary variables, right? So this is a finite recursion in boundary variables. So the averages of functions can be computed by a finite recursion for these functions. And that's a general thing, actually. If you have continuous functions given by geometric recursion on tight Muller spaces, and they are such that you can make sense of their averages, then the averages will satisfy recursion, which is similar to this one here. And so that is really a manifestation of saying, when you have functions given by geometric recursion, their averages will be given by topological recursion. Because the difference between this and topological recursion is simply just the Laplace transform in the boundary variables.
Jürgen, may I ask a question?
Yeah.
So because in airy structures, it was important that 3-point function was symmetric.
Mm-hmm.
Is it the same for this B and C?
No. So we don't have the symmetry assumption here. So you see, we have broken the symmetry by having an in boundary and then the rest out.
Yes.
So therefore we have simply destroyed the symmetry. We do know relations on ABCD that will guarantee that the output is symmetric, but we're not quite confident they are quite the right relations, okay? And so it's a different, I mean, they're not, so that the natural thing to do here is not to require that your output is symmetric, I would say. But it's an interesting question. I mean, we're still somehow working a bit on this and trying to find, the right relations that will always guarantee the symmetry. But of course, it means that you have to prove more things about your initial data, right? If you want to satisfy this. But we don't have any requirement on it as it is here, right? Okay, again, I want to really try to speed up. So this slide here just says what I was saying before. If you have topological, sorry, this slide here is just recalling the setup of topological recursion, which is not necessary. But then the theorem says that, if you have some GR amplitudes, okay, which depends on a certain parameter beta. So there's a way to twist initial data by this parameter beta. And if you do so, then there is a spectral curve, complete setup for topological recursion, run the topological recursions, get omega GNs, and then do these residues here. And then that will compute for you the limit of these integrals here, but you see the Laplace transforms here. So I don't want to dwell with this any further. It's the same thing basically restated here, okay? So let me try to push on, and I will not go through this section here, although it's very, very fun. It's a lot of fun to show that, there's something called a quantum master equation in string field theory, and to find a solution for this quantum master equation is possible using geometric recursion. So we can actually build a measurable function, which precisely, so it has to do with producing a indicator function for the subset of things where the systole is bigger than epsilon, and we were able to do that here. But I will just skip this quickly. But if we post the lecture notes, you can somehow have a look at it. I just want to try to also get to forms.
That's my another question. So please send your slides if you don't mind.
Yeah, I will do that. But what I want to show you now is an example where we use forms. So tight Muller space of a pair of pants, now where I really do remember these mark points and so on, is now bigger, right? It's in fact an even dimensional space. It has 6 coordinates for a pair of pants, and for a one-hole torus, it has 4 coordinates, the French and Nielsen coordinates. And the form that I would now like to do is I would like to take this X of the Weil-Petersen symplectic form. So that's what I take for A. And now notice that this is sort of a generalization that really works in this case with boundaries. because I have an even dimensional space, 6-dimensional here. And then I'm claiming that if you take the B from Mirzakhani-McShane and you multiply it onto this form here, where you see I stop at 2 now. So I only do the ones that are common to the boundary, and I do something slightly different on the inner one for B. And for C, I do indeed the same kind of thing. For the 2 inner ones, I have a different form, but then I do X of the one from the boundary that C still has in common with the surface. And for the for D, I simply take X of the Weil-Petersson symplectic form. And then the thing is, if you take the target theory, which is all forms on these Teichmüller spaces, and you run the geometric recursion for this setup here, you will indeed always get X of the Weil-Petersson symplectic form. And I just want to dwell.
Can I just ask, Jon,
Yeah.
that logarithmic differential at the end there is defined on the universal cover, not on the quotient, because you can't divide an angle by a real number.
Yes, but that's right, but you're taking D of it.
Yeah, but I still don't think it works, does it?
No, I mean, there's
D of it
why
it's d theta, which does make sense indeed, over L minus theta over L squared DL, but theta is not a number.
No, I mean, this is fine on the universal
You want me
cover.
to, oh, hang on, do you want me to think of theta as a complex number of modulus 1?
Yes.
Oh, very good. Okay.
Yes, just so. Yes.
Thank you.
So yeah. Yeah, that's important. But so let me just show you what are the gluing morphisms and union morphisms. So the union morphism, just like for functions, except I pull back the forms and then I wedge them. So that's very simple to understand. And then for the gluing morphisms, remember that I had this circle bundle, copies of circles, as many as I have gluing components, over the Teichmüller space where I have glued. So there should have been a little beta. It's up here. Sorry, that's missing. Oh, no, sorry, it comes here. So this is just inclusion where the boundaries agree. So that's the inclusion. And then down here, I have this circle vibration. And so the idea is simply just here, you just wedge the two, so pull the two forms back, wedge them together, pull them back to the sub-variety where they agree, and then you push forward with respect to the circle vibration. And so that's the morphism to which you have to apply to these forms here. And I also want to mention that there is actually a way that you can really make this work with seminorms. And it's quite interesting. It has taken us quite some time to figure this out. But now I know how to do it with the right set of seminorms for forms. And I must say, I think it's very, very interesting to try to understand what kind of forms can you obtain this way. Anyway, I leave that remark with you. I now want to really speed up, so I'm going to not at all touch on this, except for just noting here that I think it's tomorrow, Alessandro will give his talk, and he will talk about another target theory, which is combinatorial Teichmüller theory. There are many other target theories in development, but let me push on. Let me come back to this guy here. So here I am looking at the trace of some function applied to minus the Laplacian, where I mean the directly or Neumann Laplace Beltrami operator. And so that guy, as far as I know, cannot be written in terms of in the same sum as over geodesics, which are simple. But there is a way to write it as a sum over geodesics, which are primitive. So it means they're not run several times, but they do self-intersect. And that's, of course, the celebrated Selberg trace formula, which you see right here. So there's an overall term that, so to speak, comes from the identity in the Fuchsian group that gives you the surface. And then there are further sums that has to do with various kinds of geodesics on the surface with boundary. In this case here, I'm formulating it for surfaces with boundaries. And then there is some overall term coming from the boundary. And here, this f twiddle here is actually very closely related to f, just somehow a square root of, you know, x p squared plus 4 is the relation between lambda and f. So it's just some kind of reparameterization of f. And g is the Fourier transform of f twiddle. So this is the Selberg trace formula. But the thing is that it does not lend itself very well to geometric recursion, okay? Because at least we don't know if this satisfies geometric recursion, and I doubt it very much it does. But it does satisfy open geometric recursion. And so let me now very quickly try to go through this in the remaining, what is it, 9 minutes or something like this. So open geometric recursion is where we consider surfaces with corners as well. So you consider compact oriented surfaces with corners and with a mark point at one of the corners, okay? And then you introduce a certain quantity. Well, first of all, you say C is the total number of corners and mark points. And so there must be, so if there's no corner on a boundary component, there must be a mark point. So I'm working with that theory now. But if there are corners, the mark point has to be one of the corners. And now I define this sort of funny Euler characteristic, which is 3 times the Euler characteristic minus the number of corners. So that thing is always less. I will assume all my surfaces has the property that this is less than or equal to 0. Okay, very good. And so again, I want it so that each, the set of in mark points are, I call it C sigma minus, and this inclusion here gives me 1 for each connected component. That's what it says here. And then morphisms are as you expect. So I don't want to go through that. And then now what we want to do is, let me skip this thing about segments and so on. It's not so important right now, but what I want is now a function from this category of surfaces with corners to vector spaces. Okay, and now here is the main idea behind open geometric recursion. And so what we are going to do now is, instead of removing pair pairs, we are going to remove triangles, just like you see here. And there are a number of different cases that you will encounter in this case. And so there are 3 different types of triangles you can remove. They are sort of depicted here. It has to do with how many sides they have in common with the boundary. And in this case, none. It just has 1 vertex. And then when you start thinking about geodesics on these kinds of surfaces, what you will end up also having this move here where you remove a cylinder. So one boundary of the cylinder is smooth, but the other one has 1 corner. So it's like a teardrop. And so you have union, you have gluing and so on, same thing as before. But now, of course, your recursion becomes longer because there are more special cases. But the whole thing, the whole idea is completely the same. Okay, so let me just, what will happen is that you need to specify initial data will be an A for a triangle. You have the recursion kernels, 3 of them for a triangle. And then you have a further recursion. Sorry, you have of course, something to assign to a teardrop to a cylinder. Okay, this teardrop, which is, these should be mapping class group invariant. There is no mapping class group at all acting there. Okay, and so the thing is, again, there are some admissibility conditions of this initial data. I will not answer this right now, but I will just say that now we do exactly the same as we did before. And the theorem is that this gives you a well-defined theory, which again, absolute convergence and so on. Now the question, do we have nice examples of this? Okay, well, let's look at what we need to specify from the beginning. So let's take, again, continuous functions on Teichmüller space. And so the Teichmüller space for a triangle is this guy. Here's a 3-dimensional guy, and you can parameterize it in many different ways. But let's say we parameterize it by the angles at the corners, alpha, beta, gamma. And then what you need to have is that I'm going to constrain it in this note here, such that they lie in the interval from 0 to pi. And then the sum of them should be less than pi in order for there to exist a hyperbolic metric on the surface with those angles. Alternatively, you could parameterize them via lengths of the boundaries. And then there's the teardrop or the cylinder here. So you see it here, and actually there are several ways of parameterizing it. But for example, if you take this distance here between the inner and the outer boundary to call LC, and then I think it's L1, which is the length of the inner boundary, then that parameterizes uniquely this triangular space. It becomes an R plus to this 2. And all the other parameters you see here are actually determined by those 2 parameters. And this follows from something called the Lambert quadrilateral formulae in hyperbolic geometry. And so, okay, very good. So now the thing is, I just need to specify functions of 3 variables, alpha, beta, gamma, and I need to specify functions of 2 variables, L and C, and then they have to satisfy certain analytic estimates, and then I get functions on triangular space. And the thing is that if you take the following nice guy, so if you take A to be 1, and you take the B's to be very simple, so you fix some A0, which is an angle at the vertex in you're going to work it. Then you scale the vertex alpha here by dividing it by alpha 0. And then the most interesting guy is the guy you associate to a teardrop. That guy is some function of LC and L1 divided by alpha 0. And there is some little hyperbolic geometry trickery that you can do. So I managed to actually figure out what precisely the formula for this F is. It's given here. So this expresses F, it expresses cos of F in terms of all of this. So the true F here is arc cos of this whole guy here. And when you do this and you run the geometric open recursion, you get the function 1. So this is the Mirzakhani-McShane identity for surfaces with corners. And so now we have our partition of unity that is so important in the previous stuff. So now I continue using this. So I won't go into the proof. The proof is similar to Mirzakhani's. You just shoot a geodesic from a corner at a certain angle and you figure out what happens. But what we can do now is that we can actually introduce functions where we sum over all geodesics. So say primitive geodesics, but not simple. Now they can cross themselves. And so we consider a function where we sum over all embedded curves, all immersed curves, all closed immersed curves. We take some function of sufficiently fast decay, we apply it to the lengths, and we sum, just like before. And we take the product for disconnected surfaces, and we start with the function 1 for a torus and 1 for a triangle and 1 for a cylinder or teardrop. And then we can do F twisting of Mirzakhani-McShane data exactly the same way as we did before. Now there's a little bit more complicated here. And in fact, in this slide here, I'm assuming that F actually has this multiplicative property here. And so if F has this multiplicative property and you twist this way, what you will get is that function where you sum over all geodesics, not just simple geodesics, but all geodesics satisfies this open recursion. And so I just speed quickly past the proof of this and come back here. And so this, because if we can now use the Selberg trace formula to actually express this guy here in terms of open geometric recursion. And so that's what this last thing here states, that there is some function F here. I'm not telling you exactly what this F is, but for some function F here, we can actually show that this function here is obtained by open geometric recursion. And when you integrate this guy over moduli spaces, you will get some form of, or some recursion which only depends on lengths of the boundary. And that's what we call open topological recursion. So I think Nicolas and Bertrand has looked at something like this before, and it fits the scheme with small modifications. So this is telling you can do integrals of this type, and those integrals of guys like this are very important, for example, for understanding, statistics of eigenfunction of eigenvalues of the Laplacian on surfaces, so we can compute those by risk recursion, just in the boundary length. And also, when you look at various Poissonic string theory, so if you consider they are given by averages of such functions over the moduli spaces. And so they satisfy this kind of recursion too. Thank you.
Thanks a lot, Göran. Let's thank the speaker. For me, it was a real pleasure to see such an explicit and clear explanation of a developing theory. Questions?
Yeah.
I was wondering if people have, or you rushed past the slide about generalizations, whether people have looked at the Ilfeld case where you replace surfaces by principal bundles over a surface.
Do you mean with finite structure groups?
Finite structure group, and perhaps with discrete torsion, like Turayev has.
Right, right. I don't know. I think it's a great thing to do. I do know that covers, I mean, counting covers is something that is a big thing in TR, right?
That's a good point. Yeah.
Yeah. So I think it would be very natural to try to do this thing and work with that. So if I go back to that slide, indeed, whoa, I don't know what happened to that's my entire
Danish internet. Oh.
Yeah, so I guess I just go escape. Okay, there we go. I'm just trying to quickly get back to that slide where all the examples are.
Yeah.
So yeah, so what I've been sort of playing with is functions on moduli space of flat connections, which is parameterized by Teichmüller space. So for example, if you look at something like the Ricci potential on the moduli space of flat connections, well, then that depends on the Kähler structure. So it becomes some function from Teichmüller space into functions on moduli space of flat connections. And, you know, by Sograf and Taktitjan's work, we know that it is given by some functions of, you know, determinants of Laplacians and Selberg zeta functions. And so I'm trying to fit that into the picture as well. I think there's no problem in defining the target theories where you take coefficients in functions on moduli spaces. And so I expect that such guys will be determined by this. And then I've also been working on complex structures on moduli spaces parameterized by Teichmüller space. So there, you know, we're very familiar with that the narrow symmetry theorem says that, you know, when you have cusp boundaries, so corresponding to Riemann surfaces just with marked points, then you get an associated complex structure. But I think there is a richer picture where this works for surfaces with boundaries also, and that you in the limit recover the narrow symmetry theorem. So there, that's, and also working on, you know, boundary vectors in TQFT, because that's sort of related to this and so on, because we don't know a good geometric formula yet for the boundary vectors in you know, in the context of geometric quantization of moduli spaces. But, you know, everything here can be made to work with as far as the target theories are concerned, you know. So you can look at the target theory, which is smooth sections of the line bundle over moduli space, but then functions from Teichmüller space into that guy too, and so on. So there's really a lot of possibilities. And of course, the super Teichmüller theory, that's something I'm doing together with Nadia, and that's developing well. I think this will work, and we can fit the Mirzakhani McShane super identities into this picture also. So, and that would of course be with the aim of trying to go in you know, in superstring theory direction. So, but yeah, that's developing.
Sorry, everybody, I'm afraid we have a long program before us, and so we have to stop questions. Let us thank Göran once again.
Thank you.
And
stop sharing.
Stop recording. And
did I